Okay, so in this video, we're going to take a look at some topics that could come up in OCR paper 2. So we're looking at electricity, waves, quantum, and also looking at electric magnetic fields, medical physics, that kind of thing. So to start off with, we're going to be looking at the planetary model of the atom, where we imagine that electrons are in orbit around the nucleus like planets around the sun. So the Bohr radius of hydrogen, which is the average distance of an electron from the center of the nucleus, is 5.29 times 10 to the minus 11 meters. Calculate the electric potential energy of the electron at this distance. Okay, so hydrogen is one proton, one electron. So we can calculate its electric potential energy by multiplying their two charges together, and then dividing by 4 pi e0 times the Bohr radius, giving us an electric potential energy of minus 4.35 times 10 to the minus 18 joules. So the next question, calculate the kinetic energy of the electron at this distance. So if we imagine it to be in circular motion, we know that the centripetal force must be equal to QQ of 4 pi e0 r squared. And if we cancel the r's and divide both sides by 2, that's going to give us kinetic energy. And what you'll notice is that's exactly half of the electric potential energy, but it's going to be a positive number resulting from that. And so that gives us 2.18 times 10 to the minus 18 joules. So the total energy of the electron would be those two energies added together, giving us a total energy of minus 2.18 times 10 to the minus 18 joules. And know that that's not a problem that's negative. Things can have very easily have a total energy that is negative. Okay, so that's the energy predicted by the planetary model of the atom. So now we're going to look at the quantum model of the atom, and there's an equation to calculate the total energy of an electron in a given quantum state. And that's that the energy at quantum level n is equal to the ionization energy divided by the quantum number squared. So if hydrogen has an ionization energy of 13.6 electron volts, calculate the total energy of an electron in ground state where n equals 1. So that's fairly straightforward. We first need to convert the electron volts into joules, and then we just need to divide it by 1 squared and times it by minus 1, and it comes out as minus 2.18 times 10 to the minus 18. So comparing that to our previous answer, both models give us identical values of energy, indicating that an electron at the Bohr radius is equivalent to an electron in ground state, because they have the same amount of energy. Okay. So one of the reasons to start thinking about is why we need this quantum model of the atom. Why can't we just stick to the planetary model if they both give us the same answers? Well, that's because there are some phenomena that the planetary model cannot explain, but the quantum model can. So using circular motion and the Coulomb's law of charge, essentially the planetary model doesn't indicate that electrons can only occupy certain distances. So the planetary model basically says if they have the right speeds, they could be at any distance from the nucleus. But we know from emission spectra that electrons can only occupy certain energy states or certain radii from the nucleus because we only get certain photons being produced. So that's the weakness in the planetary model. It can't explain this idea of fixed energy levels and fixed energy gaps because it doesn't predict that those exist at all. Okay, so now moving on to another model of the atom, modeling it as a stationary wave. So helium has 2 electrons in its ground state, or inner shell if you want to go in chemistry terms. Explain how these 2 electrons can form a stationary wave by considering the velocity and wavelength of these 2 electrons. So first of all, we'll consider the velocity. So as they are in the same energy level or have the same distance, and they also have the same charge because they're both electrons, and the force they're experiencing is from the same nucleus, their velocities have to be the same from essentially making the centripetal force equal to Coulomb's law of charge. So we know their velocities must be exactly the same, which is one of the conditions to form a stationary wave. Thinking about the wavelength of a particle, so as the electrons have the same mass and velocity, according to the de Broglie equation, they also have the same wavelength. So as long as they're orbiting in opposite directions, we've got the conditions required to form a stationary wave at their same speed, in the same wavelength, and therefore the same frequency, and opposite directions. And those are the conditions we need to form a stationary wave. So we can think of an orbital with 2 electrons in it as a stationary wave. Okay. So moving on to a bit more of the photon model of light. So silver has 2 quoted values. It has a work function, 4.26 eV, and an ionization energy, 7.58 eV. Both of these are energies to remove an electron from it. So why do they have 2 different values? Because surely you'd imagine, well, it should take the same amount of energy every time, right? No. So let's first define what the 2 things are. So work function is the minimum photon energy required to remove a free electron from the surface of a material. Ionization energy is slightly different. It's the work done to remove an orbital electron in ground state from an atom. So because you're removing 2 different types of electron, that means they're going to take 2 different types of energy. And the reason work function is less than the ionization energy is the electron is free, so the force binding it to the material are weaker, so less work is required to remove it. So explain why the light received from the sun is a near continuous spectrum, but has some missing wavelengths. So when we're modeling stars, we model them as being black bodies, which means the core of them is emitting every single wavelength of the electromagnetic spectrum, just the intensities of each wavelength are different. So that's our starting point. We've got all of the wavelengths being emitted. So as those photons pass through the star's outer atmosphere, some of them are absorbed by the orbital electrons in atoms that are pleasant. And the photons that are absorbed are the ones with energy exactly equal to the energy gaps inside the atoms. Okay, so we've got some being absorbed. So when those electrons de-excite, the photons are emitted in all directions. So the photons are all traveling in kind of one direction towards Earth. Some of them are absorbed and then emitted in all directions. And that means the intensity of these photons when they arrive on Earth is going to be much lower. So we always see them as black lines, but that doesn't mean the intensity is 0. It just means it's considerably less than the other ones, which means because it's been emitted in all directions. So that's why we've got missing wavelengths. So this whole process of studying stars from their radiation is known as spectrometry. So modeling the Earth and the Sun as black bodies describe the similarities and differences between the electromagnetic radiation emitted by the Sun and the Earth. So if we're modeling them both as black bodies, the similarity is going to be that they're both emitting all the possible wavelengths of the electromagnetic spectrum. So that's going to be the similarity. The difference is the temperature of the 2. So the surface temperature of the Sun is going to be much higher than the surface temperature of Earth, and that's because fusion's happening in a star, whereas the Earth is just receiving energy from the Sun. So the way we can explain the difference is using Wien's displacement law. That says the peak wavelength, or the wavelength at the highest intensity, is inversely proportional to temperature if we can model it as a black body. So therefore, for the Sun, the peak wavelength is going to be shorter than that of the Earth, and that's the key difference between the 2 types of radiation. The wavelength at the highest intensity is going to be shorter for the Sun. Okay. So using that, explain why greenhouse gases only absorb the wavelengths of radiation from Earth, not from the Sun, and explain why in the last 200 years the temperature of Earth has been increasing, whereas before that it was constant. So first of all, There are three what we call greenhouse gases in the atmosphere: methane, CO2, and water vapor. So every single type of atom or molecule has bonds, and those bonds absorb certain wavelengths of radiation, and that's how infrared spectroscopy and all these things you learn in chemistry work. So they only absorb certain wavelengths, which in the case of greenhouse gases is the same wavelength as is emitted by the Earth, but because the photons or the waves from the sun are a shorter wavelength, they are not absorbed by greenhouse gases. So the bonds then re-emit photons in all directions, kind of the same way excitation and de-excitation works, some of which are going to go back towards the Earth and going to be absorbed by the surface, and that's going to make the internal energy increase if you're absorbing photons. So before 200 years ago, the Earth was in a nice balance. So the rate of energy absorbed by the Earth's surface, both from the sun and also from this kind of reflected radiation, if you like, was equal to the rate it was re-emitted to space. So the internal energy and therefore the temperature stayed constant, at least on average. But now we're starting to artificially increase the levels of CO2 in particular. The rate at which the Earth is absorbing or receiving energy is now greater than the rate it emits it, and that means its internal energy and temperature is rising, as has been measured over the last few hundred years and is projected to continue to do so. Okay, so that's the link between kind of radiation and global warming. To jump into something completely different, we're going to take a look at LEDs, which is again using the idea of photons. So red light has a wavelength of 700 nanometers. Calculate the energy of a red photon. That's fairly straightforward, just using E equals HF, turning it into HC over lambda. And that comes out as 2.84 times 10 to the minus 19 joules. And we're now going to link that into the behavior of an LED. So the IV graph of an LED looks something like this. For all the negative potential differences and also small positive ones, we get no current, and then we get a sudden increase in the current that is produced. So let's try and explain why you have to have a certain PD before you get a current. So what we're going to do is calculate the activation potential for a red LED. So essentially what we're going to do is figure out the work done by each electron that passes through the LED, and also figure out the work done to produce a photon of red light, because using conservation of energy, those two work done must be the same. So we can rearrange and figure out that the activation potential difference for a red LED is 1.77 volts, or that's the amount of energy each electron is transferring as it passes through the LED to produce a photon. So if we compare that to the activation potential difference for a violet LED, so violet photons have a higher energy than red photons because they have a shorter wavelength. So each electron that passes through the LED can only cause one excitation. So the work done by each electron must be higher to produce violet light. So the work done by each electron is the charge of an electron times the potential difference, but the charge is still the same because they're still electrons. So that means the activation potential for a violet LED would be slightly higher to produce higher energy photons. Okay, so to finish off, the LED is placed in series with a variable resistor set to 5.4 ohms and two identical EMF sources, each of 4 volts. Calculate the current passing through the circuit when the LED just turns on, which means the potential difference across it will be equal to the activation potential. So we can use Kirchhoff's second law, the sum of the EMFs is equal to the sum of the potential differences, to figure out the potential difference across the resistor. It will be the two EMF sources added together because they're in series, minus the activation potential of the LED. And then once we know the potential difference and we know its resistance, we can calculate its current as 1.2 amps. So final question. Suggest a reason why LEDs are far more efficient than filament bulbs. So this is all about the wasted energy. So the excitation produces an LED produces mostly visible photons. Very few of the photons produced are wasted or in the wrong kind of parts of the spectrum. Whereas the filament bulb produces mostly heat and then a few visible light photons, which we kind of deemed good enough. So it's the fact that the amount of energy wasted is considerably smaller is why we consider them much more efficient.